In this video, we are going to see some properties of the continuous time Fourier series. To define a certain property of a Fourier series, let's make some assumptions. So what are the assumptions we are going to make? Suppose x of t is a periodic signal time period capital T, so that its fundamental frequency will become which is omega 0, nothing but 2 pi by t. Then if the Fourier series coefficient denoted by k, we will use a notation x of t. If I use a Fourier series, it will give a Fourier series coefficient ak. So this notation will tell the relationship between x of t and ak through a Fourier series. So with respect to this, let's define its property one by one. So let's start with the first property, which is the linearity. It's quite simple. We are having two periodic signals, x of t and y of t, with the same fundamental time period t. Which can be represented like this: x of t, if we find out a Fourier series, it will give a Fourier series coefficient ak, and y of t, through a Fourier series we get a coefficient bk. Then if we are having a third signal, which is z of t, a linear combination of these two, x of t and y of t, as a times x of t plus b times y of t, its Fourier series coefficient will be ck, and that is nothing but capital A times ak plus capital B times bk. So it's quite simple that this is obeying the property of superposition and homogeneity. So A is getting multiplied with x of t. Similarly, on the output side, Fourier series coefficient will also get multiplied with the same constant capital A. Similar exercise will be there for y of t. So we'll get this particular Fourier series coefficient for z, which is nothing but a linear combination of x and y. Let's go to the next property, which is time shifting. So what we are having over here, we are having a y of t as the time shifted version of x of t, which is x of t minus t0. So I repeat, this is nothing but time shifted version of x of t. So what we'll get as the Fourier series, which we denoted as bk. So what we'll say, y of t through Fourier series will give us a coefficient bk, and that bk can be calculated like this: 1 upon t integral over time period t, signal is y of t, which is nothing but x of t minus t0 e raised to minus j k omega 0 t into dt. So we need to solve this integral. So what we'll do, we'll put tau as t minus t0 so that t become tau plus t0 and dt will be d tau, and there won't be any effect on these limits. So what I can say, bk will be 1 by t integral over the capital T x of tau e raised to minus jk omega 0, t will get replaced by tau plus t0 into d tau. So let's simplify. 1 by t integral over capital T x of tau e raised to minus jk omega 0 tau into e raised to minus jk omega 0 t0 d tau. Now tau is the variable with respect to which we will solve this integral. For that, this term will be a constant. So let's take this term outside the integral. So bk will be e raised to minus jk omega 0 t0 1 by t integral over capital T x of tau e raised to minus jk omega 0 tau d tau. Now it is quite obvious that this particular term is nothing but ak, because that we obtained by taking our original signal. We are just changing the variable from t to tau, but in a definite integral that is not going to matter. So what I can say, in the end I will get bk as e raised to minus jk omega 0 t0 into ak. So in the end I can say x of t minus t0 through Fourier series, what we will say, whatever the coefficient earlier was there for x of t, that will just get multiplied with this e raised to minus j k omega 0 t0. What we can say over here, still this is just a term which is getting multiplied with ak, that is not going to affect the magnitude. It is just a term coming as a angular term, rather a complex exponential. So what I can say over here, bk magnitude is same as ak magnitude. So what we can say, time shifting does not affect the magnitude of Fourier series coefficient. So I can say Fourier series coefficient magnitude are constant or not changed, though there is a shifting in the signal. Let's go to the next property, that is time reversal. So So what we have to find out over here is a time reversal. If a new signal y of t is there, which is nothing but a time reverse version of x of t. We need to find out, we need to check what will be the effect on Fourier series coefficient. So I can say now x of minus t will become summation k from minus infinity to infinity ak e raised to minus j k 2 pi by t. I just substituted omega 0 as 2 pi by t into t. So what I have done over here, t I replaced by minus t in a original expression of a Fourier series, so that I will get this. Now what I am going to do, I am going to put k as minus n, so that we obtain y of t, which is nothing but x of minus t, summation. See, there won't be any change over here because it's just a summation, and I'm having a summation from minus infinity to infinity only. The major effect will happen to this. So here I say a minus n e raised to j m 2 pi by capital T into small t. Now this is nothing but a Fourier series representation of any signal, where Fourier series coefficient will be this. So now what I can say, what effect it will have, the new coefficient that we obtain by doing a time reversal of a signal will be denoted as bk, and that bk is nothing but a minus k. So whenever we do a time reverse of a signal, what will happen? Whatever the values you obtain a minus k, that will be same for a bk. So let's club these two into one line or one statement like this. If x of t through Fourier series, we are getting ak as a Fourier series coefficient, then x of minus t through a Fourier series will get a minus k. This is nothing but a property which we say a time reversal. Let's go to the next property, that is time scaling. So what we do in a time scaling, x of t is an original signal with a fundamental time period t. Through a Fourier series, it is obtaining ak as a Fourier series coefficient. Now we need to find out, if I have a signal x of alpha t, and I am considering alpha greater than 1, and we need to find out what will be the effect on the Fourier series coefficient. So x of alpha t, Fourier series representation will be k from minus infinity to infinity ak e raised to j k. Instead of a t, I have to put alpha t into omega 0. Same I can represent in different manner like this. So if you see properly over here, what I'm having, whatever the multiplier we are having with t in the signal, that will affect only a fundamental frequency. So only a fundamental frequency's multiplier is changing, but there is no effect on the Fourier series coefficient. So what I can say, whenever we have a time scaling in a signal, there won't be no effect on Fourier series coefficient. Let's go to the next property. Rather, we should say it's a relationship, and we call that as a Parseval relationship. What is showing 1 by t integral over a capital T x of t mod square dt is nothing but summation k from minus infinity to plus infinity mod ak square. So this is called as a Parseval relationship or a Parseval identity of any signal. Now we know over here ak is the Fourier series coefficient. So left hand side is nothing but average power. That is energy per unit time. In one period of the periodic signal. Which is x of t. What I will do, x of t I will write in a Fourier series representation. So the left hand side of this particular relation will be 1 by t integral over a capital T. X of t can be written as mod ak into e raised to j k omega 0 t square dt. So obviously this is a complex number because mod will be ak only. So what I can say now, it is 1 by t integral over a capital T mod ak square, which is nothing but mod ak square. So in the end I will get this expression. And what is this? So mod ak square is the average power in the kth harmonic component of x of t. So Parseval relation can give a certain relationship. Let's discuss what that relationship is. So Parseval relation states is that the total average power in a periodic signal equals the sum of average powers in all of its harmonic components. That's what it is stating. This is nothing but a total average power, and this is nothing but a average power for individual harmonic component, and that component we select by selecting the value of k from minus infinity to infinity. So it's a very important relationship which is giving a relationship of a total average power of the periodic signal with its average power of harmonic components. So here we end properties of a continuous time Fourier series. Thank you.